opening, he showed you a diagram showing lots of active research in the Cretaceous, lots of active research in the Pleistocene. What's in between? A bloody great hiatus, which I'm now going to occupy. So I'll be a sort of a virtual paleontologist in a sort of a virtual black hole. I'm also a bit of an outlier here in that what I'm talking about is primarily based on biostratigraphy and using fossils to talk about the environment, rather than more or less the other way around, which is what most of you people do. So I'll give you a little bit of background to the research that's not going on in South Australia. In our story of Southern Australian Cenozoic, it starts because India crashed into Asia. That reorganised the global spreading system, and that accelerated, that immediately reverberated in south of Southern Australia, what was to become Southern Australia, a split through eastern Gondwana land of 50 million years old by then, spreading at less than 1 centimetre per year, suddenly going up to something between 5 and 10 centimetres per year as a direct result of India-Asia collision. Now, so Australia started drifting north, and every paleobotanist, every geomorphologist, everybody that knows anything about plate tectonics at all, says that as Australia moved north, Australia moved into different environments, and that explains the climatic trajectory of Southern Australia. They are all correct, but they are only half correct. The other half of the story is that the environments came to meet Southern Australia as Australia was drifting north. And this diagram, which is based on some work that Larry Freaks' group did decades ago now, is to show some reconstructed isotherms for the ocean. The isotherms are taken from all over, including the Northern Hemisphere, so it's a pretty broad brush story. Isotherms showing how they went through tens of degrees southern latitude and northern latitude. They went through tens of degrees latitude while Australia was drifting at 7 or 10 centimetres per year. So you can see that it's not just a case of drifting north, but it's a very much a case, at least 50% of it is due to it's meeting the isotherms coming the other way in their oscillations through 50 million years. Right, now Southern Australia can be divided up conveniently, its Cenozoic stratigraphic record, into 4 big packages or sequences. You've got an early Paleogene, a late Paleogene, an early Neogene, and a late Neogene, just 4 of them. I don't want to go into the detail of that, but I'm showing 4 big unconformities. There's one, sorry. Where's the green? Up there. You can see an unconformity between the Cretaceous and the Paleocene down there. A big one between the Middle Eocene and, in this case, the Neoproterozoic. These are cryogenian rocks here, but they're very, very powerfully eroded and dissolved especially in the early Eocene. The third one is up there in the upper right. There's a big unconformity there between the late Oligocene and the early Cambrian. And the fourth package is the late Miocene and the Pliocene, and there's a big unconformity there between, in this case, early Miocene and Pliocene. Right. The first message is it was very, very wet and very, very warm in the Paleogene. It seems that the more we find out about it, the warmer and the wetter it gets. Bob Hill nowadays seems to talk in terms of it's not just very wet, it's getting more wet every year, more wet than we can possibly imagine, and far more wet than any environment on the Earth today. Now, what's that about? Here are the the two pioneering reconstructions of global climatic change through the Cenozoic based on oxygen isotopes in planktonic and benthic foraminifer from the ocean. To show what one might expect, that in the Central Pacific Ocean, the change between the deep ocean and the surface ocean increases through time, whereas in the far south, in the subantarctic on the South Tasman Plateau, the change is much more parallel between the surface and the deep ocean. So I put a circle around this situation where the isotopic record seems to be much the same at high southern latitudes as in the equatorial Pacific. What does this mean? Could it mean a virtually zero climatic gradient from the pole to the equator? Wolfgang Berger, who put this map together, said that that couldn't be so. Therefore, it must be that other component of a isotopic signature, which is salinity. What we're seeing there, he suggested, is virtually a freshwater, or at least a brackish water lint over the southern, what was to become the Southern Ocean, south of Zeemandia in the subantarctic. A freshwater or a brackish water lint over the entire part of that ocean. So I picked up that idea and ran with it and said, yeah, that would explain why we've got extremely deep weathering extending through hundreds of metres of the continental crust in this part of the world. You've got a huge amount of water running off. It would also explain where all the silica went from this prolonged deep weathering of the Australian continent. I suddenly woke up, the silica is sitting in the Southern Ocean, in the Southern Ocean sediments, and it is what we now call Horizon A in the geophysical records of the early deep sea drilling project. Okay. Oops. That's what I want, yes. All right. Since then, it seems that both things have happened. It certainly is extremely warm in this part of the world, 70 million years ago. And also, it's very, very wet. And the main advances recently have been from the deep sea drilling by a group based in Utrecht, with some from Heidelberg, using in the same samples from the same drill holes both terrestrial and marine palynology. On the right, you've got two classical groups of dinoflagellates, Apectodinium, they call it a tropical indicator, these are the cosmopolitan there, and then you've got the cold water ones. And it's turning out that the margins of the ocean showing tropical floras at 70 degrees south on what's now Wilkesland are very consilient with what's happening offshore with the marine dinocysts, the Apectodiniums there. And that's all I can really say at this time in this particular lecture. I want to talk about the transition from the hothouse, as it's now called, the hothouse, to the modern icehouse. And the main transition took place 34 odd million years ago, and the isotope signature of what's called the OI1 right there. There's the big change. The big change is there. Until fairly recently, we had a fairly vague idea that the coals, there's an extensive series of coals along the southern Australian margin, which is shown here in a diagram from my old friend Guy Holbach, strung around the north shore of the Australo-Antarctic Gulf, And the coals were somewhat vaguely late Eocene to early Oligocene age. It now seems that the coals are nearly all late Eocene in age. He's showing a gross paleobotanical composition of them into gymnosperms, notophagus, other angiosperms, and spores. And he's drawing a contrast between what's outside the Australo-Antarctic Gulf, the break along here, what's outside in Gippsland here, and what's inside over here on the shores of the Australo-Antarctic Gulf. And you can see it for yourselves. If it weren't for this one here, it would be a very strong contrast between these through here and this one over here. Okay, well then at about 34, this all changes. And we see it up here in the coals in Gippsland, where they've done a series of ratios, hundreds of them actually. Just a quick, fairly crude, very quick ratio of the southern beach to the big conifers, the so-called pines, or the pines themselves, the araucarians such as Wallenmeyer, and so on. And you can see that the big change between that, looking very broadly, and the Oligocene here, it goes down. I suggested some time ago that it made a nice parallel with the newly emerging PalaeoCO2 curve coming from the planktonic work, people such as Mark Pagani, with the alkanones in the planktonic algae. A nice sort of, it looks like an interesting change between that, parallel between that and what's going on here. And you see over here, here's the big change between the warm, the greenhouse to hothouse world of the Eocene to the cooler world, distinctly cooler world here of the early Paleogene. Sander Huben at Utrecht, a PhD student, gave us this scenario from the late Eocene, mostly uniced Antarctica, the beginnings of ice in the latest Eocene, and then fairly quickly in the early Oligocene, we're getting the solid cover of ice on Antarctica. Now, that is, the edge of that ice would be about as far from Adelaide as Melbourne is today, fairly close by. A conflict arose. Do we see sudden cold, or do we see sudden cold plus ice? Is it a chilling effect, or is it a chilling effect plus an ice effect? And we find in southern Australia, we find evidence that it really was an ice effect, because we seem to have a pretty good glaciostatic signal in this part of the world. In the earliest Oligocene, at Maslin Bay, we find late Eocene overlain by very early Oligocene in the Chinaman Gully Formation. In Adelaide, under Adelaide itself, thanks to a lot of drilling for water and a lot of reconstructions, we find a situation like this. It's pretty distinct. This is just one example of it. To the right there, you've got almost no late Eocene. It's been chopped out in the drill hole there. There's no later. Over here, there's 40 or 50 metres of it. And by and large, it looks like there's at least 50 metres, a 50-metre down cut under Adelaide. We see it on the eastern, on the western side of this Aboriginal Basin on the York Peninsula as well. And also, not quite so spectacular, but pretty strong, Guy Holgate is showing up there in the upper right, in Gippsland, in the La Trobe Valley. You can see the coals. That diagram is upside down, is it not? Yeah. That's upside down. Cool. Okay, in your mind, turn that diagram up the other way. The coals, yeah, goodness me, didn't look like that last night. The coals have been cut out, again, several tens of metres of coals have been cut out at what Guy has identified also as OI1. So this is the OI1 surface both there and also, if you can see it, upside down there. I better hastily move on after that, haven't I? Yeah. The last thing I want to say is concerning the neogene. The problem with our neogene is a lot of it's missing. We have a very poor record between the middle Miocene and the Pliocene, and that pretty poor record applies through most of the geological environments we have. In fact, the paleobotanists have called that gap, they call it the Hill Gap, in tribute to Bob Hill. Bob takes that with a grain of salt. The idea of being celebrated as a well-known scientific black hole didn't flatter Bob all that much. Well, where we don't have the gap is right on the southeast corner of the continent at Lakes Entrance. Always a pretty wet part of southern Australia, relatively speaking. During most of the period we're talking about, very wet. But nevertheless, we can see a couple of trends. On the left over there, on the left, here's a trend based on thousands of specimens of hundreds of species of foraminifera by my colleague Quan Yu Lee. He's plotted percentage of infauna, which is a signal for the amount of organic carbon that's buried. And less is getting buried. It's drying out, it's thinning out as we go through the Miocene. This diagram covers most of the Miocene, almost all of Miocene, about 20 million years worth. The diagram on the right is using the same foraminifera in a different sort of data set, binning them into inner neritic and outer neritic, or shallow and not so shallow. Fairly rough but fairly telling, and getting a wriggly line that can be made to match in considerable detail with the global theory of glacially triggered so-called sequences. The sea washing across the continental margin, washing back again, controlled by the waxing and waning of the global ice volume. In other words, what we're seeing here is a glacial signal. Right here. Yeah, the big change from what I'm calling early Neogene, which is an informal term, although I'm intent on sort of making a bit more than that, to late Neogene, that's occurring very suddenly after the Miocene climatic optimum. And the Miocene climatic optimum would be what I'd call the last greenhouse, where the Pliocene makes a fairly good sort of second place candidate. And it's followed quite suddenly by the drying out, the aridification of Australia, the disappearance of the record, the sea vanishes, the Moravian Gulf dries up, the Euclid Gulf dries up, soon after this last big warm pulse when these large tropical type foraminifera came south for the last time, Lepidocyclona houcheni. I just want to finish here with a small homily, and that is that we have this very strong fluctuating signal through almost all of the Miocene. as you know, from time to time, some of you know, from time to time, the story goes up, were the rainforest faunas of Northern Australia, were they really rainforests, or were they not rainforests? And the argument would involve, vertebrate paleontology, it would involve paleobotany, it would involve soil science. Now, the problem with all of the arguments has been we're never quite sure where we are in the record at the required level of accuracy and refinement of correlation. So you would get Greg Vitalik arguing about what it was like in Central Australia on his soil science work, which was perfectly good and perfectly valid, vis-a-vis something Mike Archer might be saying about rainforest faunas at Riversley, right? The only problem is they didn't really know what each other was talking about in terms of time. And there's plenty of room in a diagram like this for ice sheets to come and go, and for knock-on effects from that ice sheet waxing and waning, for the climate of the entire environment, a range of environments in Southern Australia, to be coming and going again. And so we can't really pin down these arguments as yet because we don't have the time, the refinement of the time. Thank you.